Good morning, everyone. I am Pooja Dobhal, Marketing Coordinator at Cengrs, and the moderator for today's webinar on low strain pile integrity test. Welcome to the ninth edition of Cengrs webinar series. This session will provide insight into the principles, methodologies, and practical applications of PIT. We'll also explore real world examples to better understand its role in ensuring structural safety and efficiency in projects. I'm honored to introduce our speaker, Mr. Sorabh Gupta, Director of Cengrs, who brings over 20 years of experience in the geotechnical engineering industry. Before we begin, I encourage everyone to actively participate. Feel free to drop your questions and comments in the chat box, and we'll address them live during the QA session. Now, let's begin the session. Over to you, sir.
Thank you, Pooja. Please confirm if you can hear me all right.
Yes, sir.
All right. Very good morning to everyone. Today's session is on low strain pile integrity testing, also known as PIT. So the session has come from a lot of requests by contractors and customers and structural engineers who receive PIT reports and often don't know how to interpret the reports. So this workshop is actually a very practical introduction to what is pile integrity testing and how to read pile integrity reports and how to interpret them. Let's get started. Very quickly about Cengrs. For those of you who don't know us, Cengrs stands for Civil Engineers. So we are geotechnical consultants based in Delhi. We've been around for 34 years now, and you know we are supported by now a staff of 170 people, and we are very proud that we have completed more than 6,900 projects in the last few years across the Indian subcontinent. In terms of service offerings, in short, everything to do with soil and foundations. So we are strong in geotechnical investigations, geophysical surveys. We have our own lab, and we also carry out a lot of geotechnical consultancy assignments as well as foundation testing assignments. And this is a 360-degree approach to our projects. So we start from geotechnical investigation, and we strongly believe that it's important to have good quality ground data or ground characterization data, and that will form the foundation for proper analysis, geotechnical analysis, and consultancy. Uh, while that is good on paper, we strongly believe that in order to translate our designs on the ground, you also need very strong uh, QA/QC at site during installation, and that's where we have also now started providing third-party pile testing and foundation inspection services. Geotech is everywhere, so we have been serving markets across all kinds of projects, and we are blessed that we have had a lot of experience with thermal power plants, nuclear power plants, bridges, airports, and so on and so forth. And that has helped us also, to learn the intricacies of different project types and also different locations. This is a map of what we have accomplished so far. As we said earlier, around 6,900 projects in the last 34 years. We like to believe there's no part of the country which we haven't explored, and possibly, I think, by some standards, we might now have one of the country's largest subsurface models anywhere, privately held. In terms of key personnel, the company was founded by Mr. Sanjay Gupta, Mr. Ravi Sundaram, and I'm the third key director. I'm Sorabh Gupta. All of us are IIT Delhi students. We are obviously supported by a very large and competent team now who are helping carrying our vision forward. So with that very brief introduction, I want to get into the main seminar today. We will cover 4 topics. I'll start with a brief introduction to what is pile integrity testing. A little bit, not too much, of the background of the test. Spend a lot of time on data processing and interpretation as well as profile analysis. So let's get started. What makes a good pile? So to perform successfully, a pile has to tick two boxes. A, you must have adequate soil resistance. At the same time, which is the geotechnical capacity of the pile. At the same time, the pile itself has to be structurally sound. Now, these are separate requirements, and both need to be satisfied for the pile to perform as per the design. Any one, so the pile otherwise, the pile might fail in geotechnical or the pile might fail in structural. So we need both of these to work for proper performance. Obviously, if you look at on the right, a pile like this certainly will not perform no matter what the soil conditions. There are several integrity methods available to us. We are obviously today we are talking about the simplest, cheapest, and fastest method, which is the pile integrity testing or the PIT, also known as sonic logging, pulse echo, and so on and so forth. There are other test methods. So there's cross-hole sonic logging (CSL), where you install access tubes in the pile, and you can actually test down the pile. You can test to check the concrete continuity. The single hole and multiple hole sonic logging. Thermal integrity profiling is coming up. Parallel seismic is a related NDT method where you can figure out the depth of unknown pile foundations. But today, I think for our discussion, we are going to deep dive only in the simplest, the pile integrity testing, and also I think arguably one of the more popular integrity methods available in India right now. In terms of standards, the PIT in 2021 made it to the BIS standard. Also, the Indian Roads Congress recognizes the test. Uh, Plus, there's a host of international standards which are available. I really like the ASTM standard. I think it's very detailed. So, for those of you who are getting into PIT testing, I would strongly encourage you to go through the ASTM standard as well. There are two kinds of QA/QC at any project site. I like to categorize it as unplanned and planned inspection. Unplanned inspection is where we go ahead with the foundation installation at site and react when something goes wrong. And this is, I think, the worst possible way to handle our projects, because when you are reacting to failures, reacting to settlements, problems, then this is completely unplanned, and this will often cause a lot of time and cost overruns, and also it will bring down the morale of the project team. What is obviously the correct method is that the foundation, if you are ever going for deep foundations on your project, the QA/QC plan should be well thought out with all the stakeholders involved. Involve your geotechnical consultant, involve your structural consultant, your architect, so on and so forth, your contractor also. And I think the best way to do it is define in writing a strong QA/QC plan for your deep foundations. Decide what kind of tests we need to do. Uh, Carry out a very robust initial pile test program, use that as a benchmarking tool, and then define what we will do for the routine or the production piles. And this is great because when your planned inspections are included in the project specifications, this is the costing is planned, the timing is planned, the sequence of work is planned. And I think more important than anything else is that the entire team is aligned towards quality and is quality conscious throughout execution. Obviously, it's important to do pile integrity testing. You look at these piles, and this is very common. These piles are structurally incompetent and will never perform as per the design. And because piles are underground, you often don't know what's really happening inside the ground until you see the ramifications of failures in a structure itself. So the main function of file integrity testing is to very quickly identify major defects. So it's kind of like a litmus test, kind of a test where you quickly test a lot of piles and you try to figure out which are the worst piles, or try to figure out what are the kind of major defects. And that I like to since the test is inexpensive and very fast and it doesn't require advanced selection, I often say you should test all your piles and use this tool as a way to figure out, what are the construction issues at site. Are we having issues with tremi-concreting? Are we having bulging? Are we having necking? Or is there a continuity issue in the concreting? Figure out the issues at site and use that information progressively to improve and correct the construction sequence, the construction methodology being used at site, and also use the PIT results to select which of the piles should be load tested. Obviously, the worst piles should be load tested. Very quickly, the test is very simple. It really just consists of attaching an accelerometer on the top of a pile, and you hit the top of the pile with a small handheld hammer. So when you do that, this generates stress waves which go down into the pile and are reflected back up. Simple as that. And the accelerometer will measure, the waves as they go down and as they come back up. So when the waves travel a distance of twice the length of the pile and come back up, the upward traveling wave actually carries a lot of information about the impedance of, and we'll talk about this more, the impedance of the pile soil model. Naturally, if there is some defect, and this is a simplistic model, if there's a defect at some point, at some depth in the pile, then some of the waves would be reflected off the defect, and that is what the upward carrying waves will carry this information when you look at the data on the pile integrity testing monitor. Again, photographs of defective piles. This is not meant to scare you. This is actually a truism. This is, I mean, in the last 15, 20 years that I have been doing pile integrity testing, I've seen so many piles which have actually looked a lot like this, that really it's a wake-up call for all of us to fix the way in which we construct, especially board piles. That's what the equipment looks like. It's very simple equipment, handheld, light, and very robust in the field. My first pile integrity tester, I bought it around 20 years back from this company PDI in the US, and it's still working perfectly fine. It's a very good equipment. These are the accelerometers and these are the hammers. I want to point out that you get two kinds of handheld hammers, the instrumented and non-instrumented. Typically, for most cases, if you're doing a time analysis, non-instrumented hammers are good enough. If you want to get readings of the force which is impacted on the pile, and sometimes you might need that, then instrumented hammers are also available, which give you a force and a velocity signal. For today's discussion, we are talking about non-instrumented hammers where you only get a velocity signal. You don't get a force signal. I always get asked this question. So before it comes up, the question is, if I have a project site and I have so many piles, which piles should I test and how many piles should I test? And my simple answer to this is test all your piles always. If required, test them once. If required, test them again. But PIT is such a simple and quick test that it really, there's no advantage in selecting piles for PIT. Just select, test all the piles at your site and do it while the piling goes on, not in the end. Because if you test in the end, you get some bad news. There's nothing you can do about it. I want to point out, and this is really the where I'm coming from in today's workshop is I've been seeing a lot of PIT reports lately where it's almost like just a self-fulfilling prophecy. You get these reports with pile is okay, pile is okay, pile is okay, and you get a copy paste kind of a job. And really, in my experience, that's not how PIT works. Real data is not perfect. Real piles, especially board piles in soil, are not perfect. There are so many imperfections in a pile, and which is why real PIT testing and real PIT interpretation becomes often quite complex. And you have to have good practice and you have to have good knowledge in order to interpret PIT test results on non-uniform or imperfect piles. Now, possibly the most important step in PIT testing is pile top preparation. I cannot overemphasize this. If you don't have good pile top preparation and when you attach the accelerometer or when you impact the hammer, if you don't have a smooth, flat surface on the top, chances are your PIT results will be useless. You might be picking up noise. You might get random data because of crushing of the pile concrete at top. So this is, I think, the most important step, and the contractor early on has to be aligned on how to prepare the pile top uh, in order to prepare the piles for integrity testing. So this is what our piles will typically look like, right? When you're done with piling and you break the pile head, this is what it looks like. Now, if you see this loose contaminated material, this has to be removed. And I understand this takes effort, but if you want your PIT results to be genuine and to make sense, and if you want to get usable data from it, very important to remove this contaminated loose material from top of the pile until you get sound pile concrete on top. In case you have rebars which are sticking out too long, my recommendation is cut the rebars to the minimum protruding depth length required. Or if you can't cut the rebars for some reason, at least either tie them together or bend them at 90 degrees. And we'll see later why this is important, because if the rebars are ringing in a low strain integrity test, that ringing of the rebars, which is, you can't see it by the naked eye, but it's going to happen, that ringing in the rebars is going to influence your PIT test results. So you, for minimum pile preparation, you locate your pile, you clean your pile top, make a smooth surface, especially make 2 or 3 or 4 locations towards the center of the pile. You should create where you create nice, flat, smooth surfaces where you can attach your accelerometer, where you can impact the hammer. So all the piles, once constructed, should be, the latents should be broken off, and the pile preparation should be done by the contractor, so that after 7 or 10 days, you can go back and you can carry out a good PIT test. I want to point out that one of the, I think, advantages of a PIT test is it doesn't require access tubes, unlike the CSL test. So you don't really need any pre-construction decision on which pile to test. You can test any pile at any point of time, uh, and I think that's very convenient for projects. Let's talk about limitations, right? So there, I think it's a little vague, but some studies which have been carried out suggest that one of the limitations of the PIT is 30 L by D, which means you can test piles with an L by D ratio, length by diameter ratio of around 30. Now, this is a rule of thumb. It really depends on, on how the pile is formed, the concrete grade, the soil strength, the diameter, length, and so on and so forth. I, I have tested piles with an LBD ratio of 250 or 60 as well, and have managed to get good quality data. But as the LBD ratio increases, the probability of getting usable PIT data reduces. The other limitation is if you have a highly non-uniform pile, uh, with a lot of changes in impedance, usually the PIT results are very hard to interpret. And remember, we are doing a very simple test, and the data is being collected at the pile top only. So naturally, if you have a very complex situation, very non-uniform piles or piles with cracks, mechanical joints, that's going to be hard to catch. Uh, Another limitation of the PIT is that small defects or short length is hard to find. So you should only really rely on the test to catch major defects. And it's not always applicable. So, if the piles are below an existing structure, you can't access the pile top. Or in some cases, of walls and D walls, you can't really use pile integrity tests. It's not meant for that. Last but not the least, because a lot of people ask me this, PIT says little to nothing about the pile capacity. It's really the test, the intention of the test is to figure out the structural integrity of the pile. If we want to understand how the pile is going to perform geotechnically, or what kind of loads we can apply on the pile, then definitely you need to go with the statico-dynamic pile load test. So that's a quick introduction. I don't want to delve too much into the theory behind the PIT, because today I want to talk about interpretation, practical use cases. That said, in short, it's simply based on the wave equation, the PIT, and this was developed years and years ago. I think it's been maybe decades, 50, 60 years it's been since the PIT wave equation was developed. And really what it says is that, in your wave propagation, when you impact the top of the pile, and I'm going to simplify this, when you impact the top of the pile, the stress waves travel down the pile and they travel back up. C being the wave speed of the pile material, and the time that it takes to come back up would be obviously the would be equal to twice it travels 2L in a time t, and the ratio of that is the wave speed. Now, the wave speed, luckily in concrete, is fairly consistent depending on the grade of concrete and the quality of concrete. Typically, wave speeds would be around, say, anywhere between 3,800 to 4,400 meter per second. So that's a known. So when you impact the pile and you watch the wave come back up, if you can pick when it comes back up, you can actually, you are measuring time and you can infer the length that the wave has traveled. So that's a simple concept. In terms of direction, I will not labor on this. Suffice to say, if you're working in a friction pile or a free end pile, then your waves which travel down and the waves, the upward traveling wave which comes up, have the same. I only want to point out that they will have the same sign. So the sign of the velocity signal will be the same for the downward and upward traveling wave. And in this case, the positive velocity is treated as downward. As I promised, I'm not going to go much more into the theory. I really want to show you how the PIT data is processed and how to interpret. The intention of this workshop is to align users of PIT equipment and also users of the PIT report. So I'm hoping to address structural engineers, contractors, owners, people who not only do the PIT, but people who have to receive the PIT reports and make sense of it. So I'm speaking from that point of view. Uh, Look at this. So basically, this is a regular test. This is the quintessentially, this is the perfect PIT result. And this is known as, the head response. Then your pile goes, sorry, the plotting is converted to length scale. So we are measuring time, but we are converting, because we assume the wave speed, we are converting the x-axis to length scale. So this is pile length, and the y-axis is amplitude. So the y-axis really is not important. We are only caring about the x-axis, which is the length and the shape of the signal. So the actual magnitude of the y-axis is really not important to us. We're looking at the shape. So the PIT, the perfect PIT result in a perfectly uniform, well-behaved pile would have a head response. It'll have a fairly flat line along the pile shaft. And when the pile toe is there, you think of it as a reflection from the pile toe. So this is known as the toe response. The head response and toe response here, the magnitudes are matching. There are no variations along the pile shaft. So we can easily conclude that this is a good pile. Now, if you get a signal like this, where you get a signature like this somewhere along the pile length, this is at 15-meter depth, then this usually means that there's a defect or a reduction of impedance at around 15 meters below the test level. When you say reduction in impedance, then we can safely assume for most cases that there might be either a reduction in the pile cross section or a degradation of the pile concrete quality at 15-meter depth, because of which there is reduction in impedance. Now, I'm going to simplify the explanation, and this is the way I explain this to our junior engineers. This may not be technically accurate, but you imagine water flowing in a river, and where at places where the river bank, the width of the river bank reduces, the water speed increases. And this is a common experience. So I often explain that, think about it like that here, the width of the river channel has reduced, the impedance has reduced, so the velocity is increased, right? So simple way to remember this. Now you can have, in terms of basic interpretation, you look at this naturally, the amplitude of this defect would be synonymous or would be proportionate to the extent to which the impedance or the resistance reduces at that depth. So if a small defect or small necking, say, then you will have something like this. As your necking increases or your defect increases, this amplitude of this increases. So this is again in a very simple case where there is a reduction of impedance. At the same time, in some piles, you might have a pile and you might have a pot belly in between or a bulge in between. So in that case, you will get the same signal, except it will be inverted. So the velocity will reduce and then it will increase. And that, when that happens, that shows me that there is an increase in impedance at that depth. So a small a bulge, medium bulge, and a large bulge. There are two ways to analyze PIT results. 99% of the time, we are using time domain analysis, and this is good if you want to locate major defects or you want to estimate the pile profile. Sometimes, and I think largely in Europe, this is quite common, is people like to use frequency domain analysis. And this is good where you want to understand the stiffness. However, this is frequency domain analysis I found is more difficult to interpret and is largely restricted to shorter piles and good for slab on grade. Uh, That said, this is what it looks like. So the top diagram is a time domain analysis, which is what we're going to talk about, where essentially you have, your velocity versus length, right? And you get a signal like this. The same data plotted in frequency domain would give you something like this, which is known as the transient dynamic response or the TDR method. And this is good because sometimes, if you plot the amplitude versus frequency, then sometimes if you have reflections from the same defect, then I find it quite useful to shift to the frequency analysis and check, is this a reflection or are these two different defects? For the purpose of today's discussion, we will limit ourselves to the time domain analysis because that's easier and that's more common. So I want to delve into, you remember how I said, so I showed you some perfect looking PIT data, but if you actually go out to site and you do some tests, you will very rarely get these beautiful looking graphs which are easy to interpret because real data is not perfect, real piles are not perfect. Typically, we are not dealing with beautiful, uniform, consistent piles in uniform soil conditions. So data enhancements, which happens in the office when you bring the data back to the office, data enhancements play a very important part in evaluating the low strain integrity tests. So one way to reduce, the noise or the random effects in data is to collect multiple blows. What my recommendation is for every pile, you should carry out at least 6 tests, and ideally at different points of the pile. And all these test results must be averaged. When you average several test results, obviously that reduces the random effects, and you get only, the true signature of the pile in your averaged result. You have to use good quality equipment with low noise, high A/D resolution, signal processing options. Uh, and beyond that, I want to now talk about what are the data enhancements which are supposed to be made in the office or the processing of the PIT data which is done in the office. Now, pay attention because this is where things get a bit interesting. So, uh, let's go through this slowly. And you can ask, we can discuss, go back and discuss questions at a later point. Look at this data. So this is typically what a PIT data would look like when you go to site. Okay. Now you see here that unlike that ideal uh, signal which I showed you, you have a head response, but I don't have a toe response. Now, if I don't have a toe response, I can't really interpret what is the length of my pile. So what do I do here? We use something known as MA or the magnification factor. Here the MA was only 1. So I can bump up in the post-processing screen, I can use a magnification factor of say 40. And you see what that does. You observe this. So this applies an exponential magnification factor in this way, which means at the toe, the signal is magnified by 40 times because I used a factor of 40. Whereas, since it's an exponential magnification, here, the magnification factor reduces. So it is 1 at the head and 40 at the toe. So when you magnify this, you'll observe how, it just stretches the amplitude of the trading signal. And this makes sense because obviously when a wave travels down and comes back up, naturally there is some amount of reduction in strength of the signal as the wave goes down. There's some de-amplification of the signal or attenuation of the signal as the signal travels down the pipe. So this is obvious. So just like you turn the volume of your radio on high, same way you have to turn the magnification on in order to really magnify the data from the deeper depths of the pile. And as your pile length increases or as your impedance increases, naturally you may have to use a larger magnification factor in order to really see what's going on, what may not be visible to the naked eye, what's going on at deeper depth. But you observe here that when I magnified the data, I got some drift in my data. So it's not really going along the x-axis, it's kind of drifting. So let's understand this and let's understand what we can do to fix the drift. Right? You see the drift. Now the reason for the drift is again the actual reason for the drift is that it is likely that below around 50 feet, I have sorry, this is in feet. Below around 50 feet, I think we have some high resistance soils, which is why the impedance, that is the upward traveling wave is carrying, is a combination of the impedance of the soil, the surrounding soil, as well as pile concrete. So if the surrounding soil becomes dense at some depth, you get a hard layer, and your pile is going through a hard layer, then the soil resistance is also visible in this data. But are we interested in the soil resistance? No. Why? Because the purpose of the PIT is to only understand the structural integrity of the pile shaft concrete. So we need to remove the effect of the soil. And we do that by using something known as a high pass filter. So in the top graph, the one which we processed earlier, the same pile, same signal, we got some drift because the high pass was 0. Now observe what happens when I use a high pass of 300. This data actually shifts, so it pivots from the drift, it pivots back to the x-axis. Now it looks a little better. What happens when I use a high pass of 150? It looks even better. And now you're beginning to see not just sort of like a toe response, you're also beginning to see this local defect at around 50-meter depth. I want to quickly go back and I want to show you this is what the raw data look like. Right. So post-processing of data. Now, if I had not done the post-processing, I had not applied the magnification and the high-pass filter, I would have thought that this is a very good-looking, very uniform pattern, and that would have been an error in judgment. So understand that post-processing, careful post-processing of PIT data is very, very critical. Otherwise, you are going to miss some of the very important information that's in there. So now if we go from here, we have gone here, and this is the same file, the same data, number 54. Right? Let's move forward. So this was when I used a high pass of 150. If I further reduce the high pass, I use a high pass of 75. This is what the data looks like. And that's good. Now here, this is very good data. I have almost completely eliminated the effect of soil resistance. Now this signature is purely carrying information of changes in impedance in the pile shaft itself, in the structural uh, aspect of the pile itself. Now, some people might be tempted that, okay, if reducing the high pass is, giving such good values, you might be tempted to reduce your high pass even more and use a high pass of, say, very low high pass of 10. But you have to be very careful, because if you use a very low high pass filter, you end up changing the shape of the PIT results altogether. And this is very dangerous. This should never be done. Right? Because then if you alter the shape of signal, then you will miss some of the important information that it carries, and you might end up misinterpreting the data. So the rule of thumb for high pass filter is, it's again, sorry, before that, high pass filter, the purpose of high pass filter is to remove the slow drift and to straighten your curve. You can use low values as long as you are not altering the the PIT shape, the data shape. And you have to avoid very low values and remove important details, just the way we saw earlier. The rule of thumb is use a high pass filter that is no less than 10 times the input pulse width. So this is the input pulse width right here. So you should use a high pass filter that is no less than 10 times its input pulse width. So if the input pulse width is, say, 5 feet, then your minimum high pass filter should be 50, no less than that. So this is high pass filter. Now, so we have covered the magnification, we have talked about the high pass filter, and I think we understand why these two are important. Now let's look at something else. I want to show you this. Now this is the same data, right? We are dealing with the same data. This is number 54 pile, which we were looking at earlier, right? And look at this. Now tell me what's happening here. I'm using the same magnification. It's 40 here, 40 here. I've used the same high pass filter of 75 here, 75 here. But why is it that the shape of my pile is completely different? So if this was interactive, I would have liked to ask the audience this, but I'll answer my own question. The reason is another very important factor, which is the magnification delay. Now, I didn't talk about this on purpose. I want to explain what is magnification delay. When we apply remember I told you how the magnification is an exponential curve, which is multiplied by the data to kind of, kind of open up or stretch the data at deeper depths. What I did not mention is that usually we use MD, which is magnification delay, and that means a magnification or delay of 12 feet means that the magnification multiplier starts from 12 feet. So look at this graph, the magnification graph. This is MD, right? And when you get a PIT report, this graph will be built in typically, and this data will be here. So you must pay close attention to make sure that the magnification delay is typically it's around 10 time or 10% of the pile length or the anticipated pile length, right? Usually not much more, not much less. So look at what we did here. The MD of 12 gives you correct data. Now, in this one, the processing guy, what he did is he used a very high magnification delay of 75, right? And this is the magnification multiplier which he used. Now, what happens here is by doing that, by increasing the MD, he's hiding this defect, which is actually existing at around 50 feet, right? Simply by not magnifying it. So this is some of the tricks that people I've seen used knowingly or unknowingly. These are some of the tricks that people use to make bad piles look good or good piles look bad, and God knows. Uh, so all of us as people who are reading PIT reports, we have to appreciate what these numbers mean. We don't have to get into depth of it, but we must at least understand what these numbers mean. So when we look at a PIT report, we can look at it intelligently and we can ask questions or we can challenge the interpretations where we want. So the rule is you must always show the magnification function in your PIT reports, and you must not use an inordinately high MD delay or magnification delay, because then you actually end up hiding defects at shallow depth. Now let's look at this. If you actually go out on site and you do a PIT test, this is usually what the data looks like, and this is where you have to start from. Now look at this data. This is the real data which we have collected, where you see this ringing data, right? And this complicates the PIT interpretation to a large extent. Now, why does this ringing happen? I don't know. It's my guess is either more likely the pile top surface was not prepared properly. Maybe it was not cleaned or ground properly. And we are testing, if you test on loose formation, sometimes, when you impact the hammer, the accelerometer will vibrate a little because it's not properly fixed to the pile head. It could be that. It could also be that you have long rebars sticking up. So when you impact the hammer, there is low strain vibration in the reinforcement bar. And that, as I told you earlier, will show up in your PIT results. So, of course, we've collected the data. Now the question is there something, is this data still usable? Do I have to reject it? Do I have to go back and retest? Or can I still use this file? The answer in this case was yes. There is something which we can do to smoothen this high frequency ringing that you see in your PIT data. That something is known as the low pass filter. Let's look at how the low pass filter works. This is my original pile data, which I showed you earlier. And with a low pass filter of 0, if I use a small low pass filter of 4, so low pass is obviously the opposite of high pass filter. So if I use a small low pass filter of 4, you see how some of this ringing has been reduced. You increase your low pass filter to 9, and now you suddenly have a fairly good looking uh, signature of the pile. Now, I want to point out in this case, either your wave speed is assumed incorrectly or the pile length is actually short. It is seems to be around 42 feet, as opposed to I think they were expecting a pile length which was around 54 feet. So that is what's going on here. But what we must focus on is using low pass filter. You can go from here to go from here, and naturally, when you have data looking like this, interpretation is a lot easier and you make fewer mistakes. Low pass filter is great. Is there an easier and better way to smooth the curve? Good news is yes, there is. It's something known as a wavelet. What is the wavelet? It's this number here, which is WL, which stands for wavelet. So you notice we had processed the data up to this level using a low pass filter of 9. This here is we don't use a low pass filter. Instead of that, we use a wavelet of 3 feet, and that kind of achieves the same results. So your final process data looks almost exactly the same. For the record, I don't like to use low pass filters. When I process my data, I like to use the wavelet function. It's easier, and it's kind of you get more consistent results with it. Let's talk about magnification factors once again. We discussed it earlier, and we talked about how to set the magnification. The rule of thumb is set a magnification factor in such a way that your amplitude of your toe response and your head response is roughly the same. So that's ideally what we're trying to get to, and that shows me that the data is being magnified enough so that the scaling effects are taken care of. Uh, but look at this case, the question is, do I have to use the same magnification factor for all my piles? Answer is no. You can change your magnification factor, particularly if your pile lengths are different. Right? So this was a case where I use a magnification factor of 5 for both the data. These are two piles at the same site. You use a magnification factor of 5 for both, but the data looks very different, right? And why is that? Because this pile is longer as compared to this pile. So what we ideally should have done, and because of that, your magnification factor at the same length is different. It's 4 in this case, it's 2 in this case. So the thumb rule is, when that happens, if you have piles at different length at the site, use different magnification factors. So longer piles, you can use a higher magnification factor. In this case, I use 15. For the short piles, I use 5. As long as your magnification functions at similar pile lengths are roughly the same. So you see here how the magnification functions at similar pile lengths are roughly the same, roughly 4. I want to look at another case where we have a large diameter pile. And as I mentioned earlier, if you have a large diameter pile, typically, you should have various permutations of location of accelerometer and location of impact. So I mentioned this earlier, and I'll show you why that's important. Uh, Three tests for the same pile at different pile locations. So this is the force accelerometer. I put the accelerometer force together, put them both in the center, and same pile, you look at how we get different test results. Right? Question: is the middle record usable? So this looks like, this looks really bad. It looks like bad data. But it's the same pile. It's the same pile head preparations happening here. And can we use this? Now look at this. When we talk about processing, this is the raw data which we get at site. And when I use wavelet and relay wave processing, which we didn't talk about, when we process the data, this data turns into this. Right. And now this makes a lot more sense. Now look at this beautiful looking data. You get a solid head response, a solid toe response. Your pile lengths are consistent, and your data, and this is the key. When you carry out several tests on the same pile, your PIT data must be almost identical. And this is what we are getting. So good pile, no problem. We can pass this pile. We can go ahead without any problems. So somebody, this is PDI. Actually, most of these slides are from Garland at PDI. I did mention that earlier. I'm sorry. I thought there was a slide. A lot of my slides are from Mr. Garland Likens of PDI. He's been a mentor to me in understanding pile testing. These slides are his. So what they did many years ago, 1999, is they actually created a large diameter pile with some known defects, and they were checking to see if you change the location of your testing, can you catch defects at different locations on the pile cross section, right? So let's look at what they did. So they tested the pile at various in different ways and at different locations. And look at what happens is at two of these locations, they actually managed to get these defects at shallow depth at around 1 foot uh, or 1 meter, sorry, in this case. They got localized defects at two locations, which means that if you have a very large diameter pile, you must test the pile at different locations. And sorry, these graphs are wrong. It's actually one test was carried out at at the north, south, east, and west. That's what these four results are. Uh, so you can catch localized impedance changes, which might be on one end of the pile, but not on the other end. So that's what I'm trying to explain. So the lessons learned, obviously your location of your accelerometer and force impact make a lot of difference. You must test at multiple locations at the top of a larger diameter shaft. And if you like in this data, if you're able to, if you're suspecting a local defect or a major defect at shallow depth, definitely I think it's okay to recommend excavation so you can physically inspect or repair the defects at near the pile top. I want to wrap up the fairly long discussion on pile interpretations by saying that you should must use similar processing for similar piles in similar soils, right? And that means if I have a single, if I'm testing piles at a site, it's not a good idea to start varying the different processing parameters. Use consistent wave speeds, magnification factors, magnification delay, wavelets, and so on and so forth. It's not a good idea to overuse these processing tools because then you'll make mistakes. Right. Data processing usually includes averaging several blows. We talked about this. Very important to take a lot of blows and averaging them to remove noise from the data. Uh, we talked about magnification versus time. We talked about high pass filtering to remove this effect of soil. We talked about wavelet filtering to remove high frequencies from ringing. We did not talk about relay wave correction, but it is very similar to using wavelets. So that's PIT interpretation in a nutshell. Uh, the software also has something known as a profile analysis, and I just want to touch upon this very briefly. So for some of us users, looking at these wiggly lines and making sense of them is a bit challenging. So the software, the PITW software, gives the option of a profile analysis. What the profile analysis does is it considers the pile top displacement as an image of the pile impedance versus depth. Right. And that is known as the profile. So this is just a visualization tool, and this is what it looks like. So this is the actual PIT result, no doubt. We have the head response, the tail response. We've just turned this by 90 degrees. And what the profile analysis does it's a visual depiction of the pile shaft impedance with depth. That's basically what it is. So you see here, in the time domain analysis, we would have noted that this part here is sort of around 30 feet, I think, is sort of like a reduction of pile impedance. So in a profile analysis, actually draws the pile shape, if you will, and actually will model the reduction in impedance as a reduction in the pile cross section. Right? And this is great sometimes for visualization process. This is very good because then you can actually see the pile, you can visualize what the PIT results mean and what my pile might look like. So just easier to look at. Uh, and then I don't want to get into the details of how the profile analysis is done. I just want to show you really what it is, so you have a certain sway in the data because of soil resistance, right? This is exactly what we removed using the high pass filter. So similarly, in the profile analysis, first you have to remove the effect of the soil resistance. So you apply a baseline correction, which is very similar to using a high pass filter, get the data along the x-axis, and then you are able to use the profile analysis to catch these kind of defects. And this is what the data will look like. So you have your PIT data uh, in time domain, and then you have your profile, which is like this. Right? What is important to note is the profile analysis also, if presented, will also show you this is the theoretical volume of concrete which was actually consumed at site, and will also calculate what is the so you can use this data because you are plotting the pile shape. You can actually calculate, what is the, as per the PIT data, what is the likely or approximate actual concrete consumption, and then we can go back to our pour cards and compare the actual concrete consumption measured at site with what we are getting from the profile analysis. And if these two match, then that's a huge confidence booster for your PIT and profile analysis. So that's it with the profile analysis. I think I'll jump to the conclusion. We have only 7 minutes left. So in terms of classification of PIT data, some people like to use simple classification A, B, C, D. So A, grade A piles are good piles. Good piles means you have a clear toe response, so you can determine the length of the pile. There is no obvious major defect and seems to be a sound shaft. So sort of like the model PIT data which I showed you earlier, with a good toe response, a good head response, and a horizontal line in between. That's a good pile. A bad pile is where you have clear identification of a serious defect, or when you don't get a toe signal, right? And this is where you need some contingency tests or some corrective measures. There's a type C, which is possible defect, which means that, okay, we have got some PIT data and it looks like there is some defect at some depth, but we can't be very sure. In these cases, there is no shame in going back and retesting the pile or carrying out some other tests. Maybe you can select these piles for a load test, for a routine load test, or so on and so forth. There is a case D, which I think is really needs to be more to be accepted in the industry, and I don't know why in India this is not accepted, which is inconclusive data, right? And this, when I do PIT, if I test 50 piles, my practical observation on in Indian project sites is that sometimes 10 to 15% of my PIT data is simply inconclusive. And the reason for that could be maybe the pile head preparation was not good. Maybe the data simply didn't make sense. Maybe I did not get consistent PIT data from the same pile. And I think it should be okay to say, okay, I've done the PIT on 1,000 piles and I'm giving you data. I'm giving you some kind of interpretation for, say, X number of piles. And for Y number of piles, the data is simply inconclusive. I can't, I've tried retesting it. I've tried various things and I simply can't figure out what's going on. And I think for if you're working in PIT, which is such a simple or very, very simple and cheap and quick test, I think it's okay. Even if you get around 80% interpretations from your PIT program, I think that's okay. So the question is, what happens if you end up with a type B or a type C file? What should you do? So the obviously the scientific approach would be you should first compare the data with other observations. If the site is still accessible, go back and retest the PIT, possibly improve the pile head preparation before you do the retest. Uh, if you are suspecting a defect just near the pile top, and if it's possible, excavate the pile and physically see for yourself if there is actually a defect or not, and rectify the pile if there is. Sometimes we have done this if the PIT data or other data shows consistently shows some defects at deeper depths. We can also core through the pile using a hydraulic core drilling rig. You can core through the pile, and that will also give you a good. You can get cores of the pile concrete with depth, and sometimes that's good in case you have things like soil inclusion or honeycombing or weak concrete, or you have cracks in the concrete. Then a pile core can actually give you some fairly good validation of your PIT data. At times, it's a good idea, and I think this is the recommended approach: is if PIT shows some bad piles, select those piles for your routine static or dynamic load tests. Worst case scenario, if you're convinced that a pile is bad, replace it, repair it, put some other piles in it. Whatever it is we have to do, we have to have a plan in place. Ideally, this should be built into the QA/QC plan for your project. You have to have a clear plan in place on what you should do if you find a defect. So it should not be left, for an on-the-spur decision. Uh, Build your plan in the QA/QC specifications itself. That if in case the PIT data is not good, follow step 2, follow step 3. So we talked about a lot of things, and I think I'm right on time for the conclusion. Uh, I want to say what we discussed. The interpretation of PIT, really speaking, we are looking for consistent and reasonable data. We are looking for it's a very qualitative kind of a test. So you're looking for similarity or differences for different piles. We are looking for structural data, defects. We are not trying to capture geotechnical defects. You can't do that using PIT. And we are really only focusing on catching the major defects. Now, you have to remember the limitations of the test itself is you cannot catch very minor variations in pile cross section. It's not an X-ray of the pile, so let's not confuse it. It's a very simple test to really just, and I said, look at it like a litmus test to just very quickly go through all your piles and catch any major issues or major defects or major inconsistencies in your pile installation program. And lastly, to really make sense of PIT data, it's very important to look at your soil report, look at your pore cards, and it's really like solving a jigsaw puzzle. You have to put all these pieces together, and only when all the pieces are put together, then you can make sense of what's actually going on at site. The second thing I want to remind you is that integrity testing is highly dependent on the pile top preparation. I keep emphasizing this. These days, on a lot of project sites, I see agencies which are deployed at site, which are testing 50, 100 piles in a day. And I really don't, I've been doing PIT testing myself with my own hands. I don't understand how you can test 50 or 100 piles in a day and without, compromising on the quality of the raw data. Uh, and I think I don't need to emphasize that it's not, I don't think quantity is important. The quality of the PIT data is a lot more important. So spend time collecting preparing a pile well, spend time collecting good quality data, do a lot of tests on every pile. And third, spend a lot of time carefully interpreting the PIT data in the office as well. Once again, integrity testing locates only major defects. So we should not try to, many reports I've seen tend to overinterpret PIT data. I think that's not a good idea. Uh, so really the test method is meant for general interpretations. It's not meant for exact details. Remember, it's not an X-ray of the pile. Right. Uh, Integrity testing is not applicable to all situations. So, as I said earlier, it's okay to say that your PIT data is inconclusive. You have to try your best. But if you have a very non-uniform pile or you have some complex site conditions, it is possible that your integrity test may not give you conclusive results. And I think in those cases, both the customer and the testing agency have to be aligned that it's okay to say that the PIT data is not conclusive and move on. Right? It is impossible to predict, once again, load capacity. PIT is not meant for predicting pile load capacity. For that, you have to still go for static dynamic pile load tests. And when in doubt, I think if you get a soil report, if you're the user, it's okay to ask for the raw data files and get a second opinion on PIT interpretation. This is also an important step. And I think this also might, in our ecosystem, I think this kind of asking for the raw data files also might help, avoid some of the adjustments that people do in PIT testing, which really I think we all need to get together and fight back on. Lastly, invest in proper pile QA/QC, invest in the right consultant, because in the end, you get what you pay for. And with that, I come to the end. Thank you so much for your time. I'll take questions. Pooja, over to you.
Thank you, sir, for such an insightful presentation. Now, let's move on to our QA session. I request everyone to please continue posting your questions in the comment section and we'll address them one by one. So, our first question is from Matt Marvel. High pass filter, is it mandatory to reflect in the report? I have not seen such data in the report. In that case, how to know what factors have been considered?
Um, yes, it should be reported, MC, definitely. And if it's missing in a report, I think you're well within your rights to demand it. So typically, I think I use the PDI equipment and it's built into the software. So the high pass filters and all the parameters are clearly displayed in the PIT results. I think there is some equipment from other countries these days where these things are masked, and that's not a good idea. So definitely ask for the data. And as I said earlier, if you're doubting the integrity of your integrity results itself, then there is no shame in asking for the raw data files and getting a second opinion.
Second question is from Arun. Does permanent pile casing affects the result? If so, can you
Hmm.
explain it?
Uh, I don't know. I would say it does not affect your results per se. Uh, the only, I guess, the effect would be if you have a lined pile or if you have a liner to a certain depth, then typically I would expect to see uniform pile shaft at least in the lined portion. Right. So a good check is, if you get PIT results and if you are seeing, variations in the area which is lined, then, I might suspect the PIT data and I might suspect, what the data is telling me. So typically in the lined pile, you get a fairly uniform cross section. I hope I answered your question.
Uh, Thank you, sir.
Yes.
Next question is from Anjanka Kadam. Concrete grade of pile is any consideration for report preparation?
No, Ajinkya, we don't care about the concrete grade as much. The possibly the only effect that the concrete grade will have is that your wave speed of your stress wave would be different. So a higher grade concrete typically will have a higher wave speed. But since we assume the wave speed, and we typically assume the wave speed not only based on the grade, but also we eyeball it, by when you look at the PIT data, usually you'll assume the wave speed in such a way that, you kind of eyeball it, adjust the wave speed so that, your toe is based on the toe response. So it doesn't matter. And then you can use the same wave speed for the rest of the piles at the same project as long as the concrete grade is the same.
Thank you, sir. Next question is from Akshat. What type of piles are best suited for PIT? Example,
All
cast and
piles.
cement.
Yeah, all piles, Akshat. You can test all piles for PIT. Naturally, if you have precast piles, the possibility of changes in cross section are almost nil because it's a precast pile. So in a precast pile, PIT might be done to figure out if there is damage at any particular depth. Right. So in a precast pile, the only fear is if you have a precast driven pile, then the only danger is that sometimes, when you're driving the pile, you end up breaking the pile at certain depths. So PIT is good. If you haven't caught that during the driving process, then PIT could be used to figure out the depth of the defect or the crack. Otherwise, I think especially in the Indian context, most of the PIT we are doing on board cast and steel piles because that is where, honestly speaking, that is where most of the structural defects actually take place. So yes, it can be applied to auger cast piles, precast piles, board piles, all kind of piles, no problem. But possibly the application is mostly for board cast and steel piles, the strongest application.
Thank you, sir. The next question is from Kirti. Sir, you have mentioned about the thumb rule of using height 10 times of the pulse width, but how to know the pulse width from the PIT data?
Okay. Just eyeball it. Kirti. So when you look at, let me show you. If you look at any PIT data, hold on. Here, right? So if you can see my screen still, if you look at this PIT data, so this, sorry, hold on. Okay. So from here to here, so around, this is meters. So from here to here, around 2.5, 3 meters is the pulse width. Yeah.
Next question is again from Matt Marvel. In one pile, I have seen rebar protruding more than 3 meter. Now, client is doubting whether rebar full insert in the pile. Is there any method by PIT we can ascertain that rebar have been fully embedded?
No, you can't, my friend. I don't understand. So, but see, I want to say this. Testing sure is not, how do I say this politely? Testing does testing is not a substitute for good workmanship at site, right? So I think we need to understand this. Good engineering, good workmanship at site, that has to be there. So your piling guy and your supervisors and your operators and your labor, they have to know what they're doing. So good, normal, good practices for pile construction like cleaning the pile bottom, flushing out the pile bottom using trimming concreting, making sure your cage goes all the way down to the bottom. These things these things cannot be replaced just because we're doing testing. So the testing assumes that the construction team has already done a good job and has paid attention and has already tried their best to install the piles as well as possible. Right? But in your case, it seems to me that the construction team simply did not do a good job. If and why should the client have a doubt when when the pile is being cast and the cage is being lowered? This is something which should have been known at the time of piling. Right? So there is no test for it. PIT can't solve for this. Mhm.
Next question is from Ekta. Sir, is there
Yeah.
any wavelength frequency we have to consider according to grade? If any, please share.
No, no, no. I think I'm not sure what you mean by wavelength frequency. Uh, are you talking about? Okay. No, again, the concrete grade does not affect the processing parameters which you use. The concrete grade primarily only affects your wave speed, right? I don't know. I didn't understand the question well enough. So please ask me a follow-up question. I don't think I got your question, but we'll move on in the meantime, Pooja.
Okay, sir. Uh, next question is from Satyam. What factors influence the accuracy of PIT results? Example: soil conditions, pile material.
Yeah, all of it. So your uh, well, if I talk about accuracy of PIT results, Satyam, I think the key things to take care of, as I mentioned, is number one, good quality pile top preparation. So this is the most important factor. If you don't spend a lot of time and effort on your proper pile top preparation, right, you are not going to get any usable data. So this is step number one. Step number two is good quality raw data collection. So, your PIT agency has to be aligned, and, your ask also should be same. Don't ask him to do 100 piles in a day. Ask him to do, maybe 25, 30 piles in a day, but ask him to spend time at each pile and take several data sets, average the data, spend time making sure that the accelerometer is affixed to the pile top properly so he gets consistent results at site itself. So this is step number two. Step number three is invest in a PIT consultant who knows what they're doing. They're not simply in the business of producing PIT reports. They should be engineers who know what PIT means. They should be able to interpret and process the PIT data properly, and they should also be capable of correlating the PIT data with your soil report, with your pore cards, with your load test data. So really, as I said earlier, understanding deep foundation QA/QC is like solving a jigsaw puzzle. Your geotechnical consultant must be completely on board for this process, and there has to be someone who kind of, understands the soil report, understands the design, understands the QA/QC reports, and somebody who's, making sense of all of this. So I think these are the factors, in my opinion, which affect the accuracy of PIT results the most. Of course, other things which you mentioned, like soil conditions, pile material, concrete continuity, these also affect the accuracy of PIT results. And obviously, if you have poor pile top preparation, if you have very dense soil, if you have very non-uniform pile shaft, then PIT results will get harder and harder to interpret, and maybe even inconclusive.
So, next question
Yeah.
is from Chintan. Sir, sometime in coastal or river portion, casing insert for pile casting. So, any identification come in PIT graph in waveform?
No, Chintan, not really. You can't really figure it out in the PIT data. So, but again, as I'm saying, if I don't know what is the purpose of this test, but if a casing, permanent or temporary liner has been installed, usually you'll find that information. You should find that information in the pore cards. So PIT will not give you this information.
Next question is from Muthu Kumar. How averaging of data is done?
So very simple, Muthu Kumar, the software does it for you. So usually when I'm doing the data collection, Then in the pit collector, when I'm collecting data on site, there is an option that how many data points I want to average, right? So I usually like to use 6 or 10 blows minimum per pile. So every time I fix the accelerometer and hammer, I will hit consistently. I will try to hit 6 or 10 times. So on the screen, I will see, say six number of blows, and then the software will average these blows. So in when you import the data in the office, you can either look at the individual blows or you can just import the average signal. So the averaging is done by the software, in short. It's just a mathematical average of the signals.
Okay, sir. Next question is from Kirti. Is there any particular wave speed range for different concrete
Um,
grades?
Typically, Kirti, anywhere between 3,600 to 4,400 meters per second. It will vary. So, what I usually like to do is I pick up the wave speed when I test at site. I pick up my best looking results, like this one here, right? So if you see this result here, so this is a fairly good looking result with a good head response and a good toe response. And I'll move this line here and move this line left and right until I get a rise to rise. So see these blue lines? So this marks the beginning of the head response. This marks the beginning of the toe response. I'll move this line left and right until it's kind of at the beginning of the toe response. So once I've done this, obviously the software will back calculate based on this length, right? It will and then I'll use a wave speed in such a way that it matches. So here you see the wave speed has been adjusted to 3962 meter per second. So when I use input this wave speed, then kind of I get this the toe response at the right location. I hope that made sense.
Next question
Yes.
is from Math Marvel. For say 1 meter diameter pile, exactly where the hammer to strike for getting accurate results? At center, away from center, or multiple locations?
Thank you. Very good question. My answer is, and I think I mentioned this somewhere in between, is test at various locations. So start by testing the center, right? And then observe the pile head and use different permutations. So you can kind of move. So if you fix the accelerometer in the center, I would first carry out one test by impacting the hammer near the accelerometer in the center only. Then I'll carry out four more tests, one at the north edge, south edge, east edge, west edge, right? And then look at all this data and make sure that it is consistent. Every pile, if tested properly, no matter where you fix the accelerometer or fix the hammer, that pile will have its own unique signature. So no matter when or how many times you test the pile or at what location, the shape of your PIT data must be consistent. But if you're testing the same pile using a different equipment or at a different time or at a different location, and if you get inconsistent results, something is wrong. The pile, I call it a signature because that shape of the PIT data is unique to that particular pile, and it must always be unique. And that's a good way to understand if your data is truly representative or not. Is test many times at many locations until you are assured that your data is consistent and repetitive.
Thank you, sir. Next question is from Arun. Can the toe response be higher than head response? If our curve shows that way, can I assume there's a usage of higher MF than required?
Yes, you are right, Arun. Yes, typically toe response would not be higher than the head response because of attenuation of the stress waves. So if you see that, most likely they've used a very high magnification factor, which needs to be reduced. Ideally, use a magnification factor to such an extent that the toe and head response are amplitude is consistent.
Um, Next question is from Rutvik. So, what is the hammer weight for 750 mm diameter of pile, 120 1200 mm and 1500 mm diameter of pile? Hammer weight affect the PIT
Yeah,
data?
yes, they do. I did not show that. Hold on. If you bear with me, I'll try to find. I have hidden some slides because the presentation becoming too long. Uh, I can't find it. Oh, okay. Let me just wing it. So Your yes, your hammer weight. So you we I use typically like to use different sizes of hammers. First of all, it's not hammer weight is not that critical, but you use a 3 pound hammer, a 7 pound hammer. So I usually take a bunch of hammers to site, right? Uh, and the reason I take different hammers is so you have to understand the large hammer or the heavy hammers will be able to impact the pile harder. So the waves can travel. If I have a long pile with a long L by D ratio or a large L by D ratio, I will typically use a large hammer first because then the wave will be able to go all the way down to the pile bottom and reflect back up. So it will carry more data up to deeper depth, right? So and after I use a large hammer, I will also usually do a repeat test using a small hammer. Why? Because small hammers will be able to carry more detail. So while large hammers will have more penetration with depth, small hammers will have carry more detail with them. So my suggestion is it doesn't really depend on the dia, it depends on the L by D ratio actually. So if you have a large L by D ratio, start using larger hammers as well as a smaller hammer. That's that's my response to this.
Next question is from Math Marvel. If below cutoff there's a weak concrete due to bentonite mixed concrete, we will remove the weak portion, say 3 meter below cutoff. How to build up? By simply pouring concrete, will get same pile results, pit results. PIT.
Uh, well, no, if below cutoff, first of all, this should not happen, MC. Right? So you should not be having weak concrete below the cutoff level. Now, if you really have a weak concrete below the cutoff level, then I think you'll have to build it up, and I think you'll have to get it designed, make sure that the connection between the original pile concrete and the new pile concrete is good, and you have to make sure that it's properly connected. Then yes, definitely you can. This is a rectification. First, it should not happen in the first place. This is the rectification. If you have this situation, then definitely remove the weak concrete, and then you have to repour concrete and make sure the connection between the old and new pile is good. But I don't know how well this will work. It's not recommended.
Um, Next question is from Kapil. How can PIT results be combined with other tests to enhance overall foundation analysis?
Very nice, couple. I don't have time to cover this in detail. I will encourage you to go to our company website, Cengrs.com. And when you do that, you will be able to go here, Cengrs.com. You will be able to go to publication section and look for a paper called Identifying Defects in Deep Board Piles. It's one of my favorite publications. You see how we have used PIT, PDA, static pile load test data, and all kinds of test data together to kind of piece together, the story of what has happened at site and understand your foundation performance. But that's a good question. It should be. The short answer is yes, you should. Thanks, Muthu Kumar.
Next question is from Anjana. What are the cost implications of using PIT compared to other methods?
So PIT is the cheapest, no, Anjana? PIT is cheapest, fastest, no-brainer. So it is the cheapest possible thing you can do. Typically, a pile integrity test would cost only a couple of thousand rupees per pile. So it is I love it because if it's cheap, then and it's quick and it's easy, then you can actually go and you can very quickly test all your piles at site while the piling is going on. So again and again, I say it's don't use it like a conclusive report. Use it like more of an indicative report to do pile integrity and use the PIT data to course correct your piling methodology or to decide which of the piles you need to select for further testing, for other integrity tests, for other load tests, and so on and so forth. Thanks, MC.
This is the last question we are taking today.
Mhm.
And, this is from Neha. What steps should be taken if a pile fails the integrity test?
Good. So I think step number one here, make sure the pile has really failed the pile integrity test. Right? Is it the pile which has failed, or is it the test which has failed, or is it the fellow who's interpreting the test results, has he failed? So for me as an engineer, this is always step number one. Right? Let's not jump to. Sometimes we tend to overreact. Ki, oh my god, my pile has failed. Uh, you know, so go back, retest, change the agency, change the equipment, change the interpretation, and make sure that the pile integrity test is really telling you a sad story. Now, if your pile integrity test is definitely giving you a sad story, then naturally the next thing to do is the simplest thing to do is select that pile for a routine pile load test. If you have static pile load test arrangement at site, ideally do that. If you don't have it, you can just go back and do a high strength dynamic pile load test. I like the high strength dynamic pile load test option because it's faster, cheaper than a static pile load test. And also because apart from the load settlement curve, a high strength dynamic pile load test also carries with it information on the pile integrity, right? So instead of using a chota hammer, you use a bada hammer to hit the same pile. So now I will also be able to compare the integrity results between the low strain and high strain tests and make sure that I'm getting consistent results. So this is usually the course. And then again, if that also tells you a sad story, then core the pile, replace the pile, add additional piles. And there's a full, there should be a full protocol in place during in your QAQC plan on what to do if the PIT test results are not encouraging.
Thank you, sir, for addressing these questions with such
Yeah,
clarity and depth. And to
I
all our
try.
attendees, thank you for joining us today's session on low strain pile integrity testing. Your active participation and curiosity have made this event truly valuable. Before we wrap up, I'm excited to announce our next webinar scheduled for 18th January. In this upcoming session, we'll delve into the geotechnical role in the construction of the Ram Janmabhoomi Temple, Ayodhya. And this promises to be a fascinating discussion on one of